In this lesson, we're going to see how to apply Kirchhoff laws. The first 5 points we've already done in a previous video in which we have to prove series and parallel combination rules and regulations. We've already done that. So, but I will go over what the first and second law actually are trying to tell you. The first law of Kirchhoff is actually trying to tell you that whatever current is entering, let's say, a single junction, and if there are multiple branches going off from that junction, then the sum of current entering the junction will be equal to the sum of current leaving the junction. For example, in terms of mathematics and algebra, if this is I1, and let's say this is I2, and let's say this is I4, and let's say this is I3, I can very clearly see that this current is entering this junction, followed by this current is also entering the junction, just like a traffic example. And I2 is leaving the junction and I3 is leaving the junction, right? So I can see that I1 combined with I4 is entering the junction. So sum of the current entering the junction is equal to the sum of current leaving the junction, which is I2 and I3 over here in this situation. This is Kirchhoff's first law, which says that this is conservation of charge, or you can say electrons. So if, let's say, 5 amperes of current is entering from this side, and let's say 4 amperes of current is entering from this side, that means that 9 amperes of current is actually being contributed by I1 and I4, right? So 9 amperes is coming into the junction. So the current leaving the junction should also be 9 amperes. It could be in any combination. For example, it's possible that this I2 is 2 amperes. Then we can very well guess that I3 must be 7 amperes. So 2 plus 7 should give me 9 amperes. So current entered the junction should be equal to the current leaving the junction. This is Kirchhoff's first law. Kirchhoff's second law is about energy, right? So it's a consequence of conservation of energy. What he's trying to tell you is, simply put, that the energy of producers, what are the producers or who are the producers, cells or batteries, is equal to the energy of consumers. Who are the consumers? There are two types. Okay, so the first one is actually the resistor or reverse connected batteries, right? So cells and batteries can also be one of the consumers if they're connected the other way around. Let's look at that example, what I'm trying to say. But simply put, producers equal to consumers. Simply put as that. And energy, although when you go towards this understanding, you see that the second law is basically dealing with voltage. You see, sum of voltage around the loop is 0. So what does that mean? It means that voltage provided by the batteries is equal to the voltage consumed by the load. And since voltage is equal to work done by charge, we can very well see that joules per coulomb, where this concept of energy actually comes from. Because voltage is energy, right? Okay, anyways, now what do we mean by this battery can be a consumer? You see, if I connect a few batteries like this, I can see that they're connected in the alternate polarity. So that is positive, minus, plus, minus. And if each one of them has a voltage of 2 volts or an EMF of 2 volts precisely, this can be equated as a battery that has an EMF of 6 volts. Because all 3 batteries, considering conventional current, are trying to cause the direction of flow in this direction. Since all 3 batteries are trying to do the same job, I can combine them to look like a single battery, just to simplify the circuit, right? Okay, so what if the batteries were connected in this way around? Let's say 2 batteries are connected this way, and 1 battery is connected like this. Again, maintaining that they are having equal EMF to simplify the situation. Otherwise, they can have different values as well. I can see that this is positive, negative, positive, negative, negative, positive. Now notice that one of the batteries has the opposite polarity to the rest of the 2 batteries. Now how to add them or think about them? So the first battery says that the current should go towards this side. Now we're considering conventional current. Of course, conventional leaves from the positive terminal. The second battery is also trying to do the same job, current leaving from the positive terminal. The third battery is trying to cause the flow of current in the opposite direction like this. So even if we had an imaginary circuit, for example, like this, some resistors were a part of the circuit like this, I can see that these two batteries, battery 1 and battery 2, are trying to cause the direction of current in this direction, and battery 3 is trying to flow the direction of current in this direction. So in turn, I can say that two batteries are working together. One battery is opposing that. So it will be 4 volts by combining these two batteries minus this battery, which is acting against it. So what are we left with? We're left with effectively only 2 volts in the circuit. Now, coming back to the point, energy of the consumers. Now, resistors we know are going to consume energy and convert it into heat or respective work done. If it's a light bulb or a fan, or let's say you're trying to charge a battery, whatever that is. But batteries connected in the other way around are also going to act like a consumer, right? So when we summarize all of these things, simply put, as basic as it can get, it's all about energy. Provider should be equal to consumer. Simple. This is the second law. Now we're going to use these tricks and tips to solve questions, right? And by the way, the proof of series and parallel resistors, this has been covered in the first part of the video. I will add the link in the description if you want to go through that. But in this video, we are just going to focus on how to use Kirchhoff laws and how those questions are going to come in the examination. You can see where the question has been picked from, and you can pause the video to read the question for yourself and try to figure it out on your own. Okay, let's try to solve this. As I've explained to you earlier, that voltage is actually work done by charge. So I'm going to deal with voltage in terms of pure energy and not look back. Simply put in that regard. Okay, so 20 volt rise means that 20 volts or 20 joules has been given or have been given to a charge or an electron. So that is moving in this direction like this. When it encounters this branch, it realizes that it can divide into these two branches. It divides, and the electron reaching at this terminal, let me zoom in. The electron reaching at this terminal, because it has not encountered any resistor so far, it still maintains 20 volts of energy, right? Okay, so electron reaching these two terminals has 20 volts. This is 20 volts. This is 20 volts. Now he says 7 volt drop. It means that this component has used that energy or has removed that energy from the voltage or from the electron. So at this terminal, I will have 7 volt less. So 20 minus 7 gives me 13 volts. Now, when I move forward from this point, I realize that this is the negative terminal. Most likely, this is actually 0 volts, and this is actually 20 volts. So this terminal will be at 0 volts. Okay, so the drop, or you can say the voltage consumed by M, should be 13 minus 0, or you can say 13 volts. L is consuming 7 volts, and across this whole combination, we can see that 20 volts are being consumed in this manner or in this fashion. If we go to the second branch, we realize that the electron entering the branch is 20 volts. Okay, but what's the voltage at this point? How can we figure it out? It's it's a bit tricky, but let's try to do that. You see, electron reaching at this point is 13 volts, right? Now, the electron going through the branch N is losing 4 volts even more. So 13 minus 4 makes sure or makes that this terminal is at 9 volts. Okay, and this terminal is at 0 volt because this is where the electron goes back after being completely drained of its energy, right? Now, I realize that this is 9 and this is 0, so this must be a potential difference of 9 volts, okay? And this must be a potential difference. Now, what do we mean by potential difference? It's the difference of energy between two terminals. So the electron entering at this point has 20 volts, and the electron at this point has 9 volts. So what's the potential difference? That's going to be 11 volts for P, 9 volts for Q, and 13 for M, and 7 for L. Now, I've solved the whole question. It's possible that some things are going to be asked. It's possible some things are not going to be asked in this MCQ, but I've solved the whole question so that you can develop the concept and use it somewhere else. Now, what do we see over here? What's going to be the answer? You can pause the video and try to figure it out on your own. You will realize that M is supposed to be 13, so it could be option B and C. P is supposed to be 11, right? So it could be, it's going to be this. Now, of course, no need to check for Q, but for the sake of understanding, we've done that as well. So Q was 9. So this is the answer. So option C is the answer for this. And how were we able to figure this out? We were able to figure out this question based on Kirchhoff's second law. that energy provided to the system will be utilized in the circuit, and coming back to the circuit or a complete loop, the voltage is supposed to be 0. Provider or the giver is equal to the consumer, whatever the consumers were in this situation. Okay, all right. Moving on to this question, this is Kirchhoff's first law. Current entering a junction will be equal to the current leaving the junction. Now you can pause the video and try to solve the question on your own, and then I can help you how to do this and develop tricks for that. Okay, so what he has given us, what is he going to give us? He's given us one piece of information that A1 is 0.6. So this branch has a current of 0.6 amperes. Now notice that this is positive and this is negative, which means that considering conventional current, the current is moving in this direction, and then when it reaches this branch, it goes towards this side and some of it goes to this side. Then that current enters this branch and some of it goes to this branch and then enters this branch. Okay. We understand that 0.6 is the reading of A1, and he says that the resistors are identical, which means that if this is R, this is also R, this is R, this is R, R, and R. We have to develop these relationships from the parallel combinations that we've already done, that voltage remains the same, but the current divides. So V equals to IR. I have I equals to V divided by R. Now, since voltage is same across all resistors, across all combinations, not across all resistors, but across all combinations and branches, we can develop this relationship I equals to 1 over R, or I proportional to 1 over R, which means that the branch with the highest resistance will receive the lowest current, and vice versa. So if in this branch there are 2 resistors and the current is 0.6, in this A3 branch I can see only 1 resistor, which means that the current should be doubled in comparison to this branch, right? Because the resistance is halved. Why? There are 2 resistors, so the resistance is effectively 2R. In this branch, it is only 1R. So the current in this branch should be doubled, or at least 2 times the current in the second branch, right? So if the resistance is being halved as from 2R to R, then the current should be doubled from 0.6 to 1.2. So I can very well guess that in A3, let's say this is A1, this is 0.6. In A3, this is 1.2 amperes, and let's try to cancel some options if they are possible, if that's possible. So A1 is not given, right? Because it's already given the question. A2 is still, it's the current of the battery, so we can't figure it out. We have to look at A3. A3 is supposed to be 1.2. So that is option D. Now, luckily for us, there is no 1.2 in the other options. So, but still, let's try to figure it out. We understand that this branch should have a current of, let me clean this up. So we understand that this branch should have a current of 1.2 based on the ratio method that we've developed from the parallel combination. This is 0.6 amperes, and this is supposed to be 1.2 amperes, a single resistor, right? Now, this helps us to figure out the current of this branch. You see, in that branch, there are 3 resistors. So if the resistance is 3 times high, then the current is going to be 3 times less because they are inversely related. So 1.2 divided by 3 gives me the current of A4, which is going to be 0.4 amperes, right? So it's going to be option D very clearly. Let me show you an animation for this, okay? This is exactly the question that we have over here, and we can see that at this point in the circuit, there is no current. If we close the switch, we can see the current is flowing, right? And let's place the ammeter at certain point. So in this point, we can see that the current is 0.6. Okay, this was mentioned in the question. So at this point, the current is going to be doubled, 1.2, because the resistance is single. As opposed to this one, there are 2 resistors over here, right? Using this idea, I can go to this branch, the 3 times the resistance, 3 times less current is going to be 0.4. Now, since I have the current of this branch, I have the current of this branch, and I have the current of this branch, I can simply add them together to find out what's the current of the supply, which is going to be 2.2, right? Okay, I hope that we understand this question now. Okay. All right. Moving on to this question. This is from P2, and this is question 5 from October-November 2017, paper 21. I'm going to explain to you the shortcut, or you can say the technique, how to solve this question, right? Otherwise, there is a proper method to do this job. The proper method I've applied is going to be on the last question, which is this one. I will show you how to apply Kirchhoff laws, but since this is an MCQ, we have to learn the technique as well. We have to learn the shortcut. But anyways, I will explain that technique over here. But let me explain to you how to do this in a matter of seconds and not waste any time. Okay, so let's see what's what. So we understand, we look at the question, we look at the variables. These are very important because we have to refer to them to understand what loop the examiner wants us to solve. Okay, all right, I'm pausing the video. You can draw this circuit on your notebook and then you can come back to this later. All right, so let's look at the first part. He says using Kirchhoff laws, he's not mentioning first or second because that's going to be on you. To state relationships. Now he's asking you to state, he's not asking you to solve. State relationships between the equations using I1, I2, and I3. Now, since this is only dealing with current, I suggest, or I think this is going to be about current and the first law, which is conservation of electric charge. Okay. All right. So I1, I2, and I3, what are they doing? So I pick out this junction where I can see that all of them can be simplified or it can be carried forward. So I3 moves like this. So I3 is entering the junction over here. I1 is leaving the junction, and carrying I2 at this point looks like I2 is also leaving the junction. So I can very well understand that I3 is entering the junction and I2 plus I1 are leaving the junction. Okay, so if you don't want to do it this way, you can do it this way as well. If you look at junction W, you can see that I3 is leaving the junction, I2 is entering the junction, and I1 is also entered the junction if I carry it forward to this side. Respecting, of course, the direction given by the examiner, we have to accept those directions as it is, okay? Because we didn't make them, he's giving us information on his own. So let's accept it as it is. So on W, I understand that I2 and I1 are entering the junction. So I1 plus I2, sum of the currents entering, equals to sum of the currents leaving, or the traffic leaving the junction. Again, if you see that this is just a matter of representation or making the subject of the formula, they're exactly the same. Okay, so I am going to write down I1 plus I2 equals to I3. Whatever suits you, it's okay. Don't worry about it. Now let me clear this out because we have to do the second parts as well. Okay. All right, moving on to the second and third part. In the second part, he says, B part, he says, use E, E1, E3, R1, so on and so forth. How to solve this question? The most important part is going to be how he is referring to this loop. The way he refers to the loop is going to give you the indication what is the positive direction of current. What direction of current will be taken as positive? Which batteries or which cells will be taken as positive or should be taken as positive? So it's W, X, Y, Z, W. Let's go back to the diagram. So it's W, X, Y. So it's moving like this. W, X, Y, Z, right? So it's W, X, Y, Z and W back like this. Now this loop labeling from the examiner tells me that this is the direction of current I should take to be positive. So this I3 will be taken as positive because it's the same direction. This I1 will be taken as positive. It's the same direction of the loop. And what about batteries? I have to figure out whether the batteries are doing the same job or not. So if I look closely, I can see that this is the positive, this is negative, this is positive, this is negative. The battery is trying to flow or make sure that the current flows in this direction. E1 is also trying to make sure that the current flows in this direction. Again, these directions match the direction of the loop mentioned by the examiner. Okay, I'm reminding you, this is not science. This is not pure physics. This is the trick to solve these questions. If you want to understand the complete in-depth analysis of the Kirchhoff law, then you'll have to wait till the end of the video. You can just skip to this question and hang around how actually Kirchhoff law works. But anyways, let's learn the trick because this is a fail-proof method. You can apply this on any question, you will find the results. Okay, so let's make the equation right now. Over here, I see that both batteries are helping each other, or you can say they're both causing the direction of current to be exactly the same. So using the second law, the idea was that the producers are equal to the consumers, or the batteries are equal to the voltage of the resistors. Okay, fine, no problem. So who are the producers? E1 and E3 are the producers in this loop. So I will add E1 with E3. Why? Because they're doing the same job. How did I figure out the job? By looking at their polarities. All right. Okay, moving on. Now I move to the consumers. Who are the consumers? Resistors are the consumers. And I know that if I want to find out the voltage of a consumer or anyone, I need its current and resistance, V equals to IR. So I3 current is passing through R3 like this. So the consumed voltage will be I3 R3. And I have to take the current to be positive. Why? Because the loop direction and the direction of the current mentioned by the examiner are in the same direction. So there will be a positive, right? So no need to write positive, okay, because of mathematics. Okay, moving on. Do I find another resistor? Yes, I find another resistor. So this will again be plus I3, again I3 carried on to this branch into R4, which will be like this. Then I move forward in this loop, I realize that there is one more resistor missing in this loop. There is no resistor over here, so no need to mention this one. No, it's okay. So I1 exactly the same direction, R1 exactly the same direction, right? So this is going to be plus I1 because the label is I1, and that is passing through R1 into R1. Now when you go to the marking scheme, you will see that he's actually combined I3 in this way and taken common. No problem. So this is going to look like this. E1 plus E3 equals to I3 into R3 plus R4 plus I1 R1. No issues in that. Okay. So it doesn't matter. Okay. All right. So I hope that we understand the trick. Okay. I will solve another question for using the trick as well. Okay. So moving on to the C part. Now, again, paying attention to the loop is very important because it tells us which one will be positive, which one will be negative. So I'm erasing this, okay, so that we can solve the next part of the question. I'm keeping the solution on the left side as it is so that you can refer to this again and again. All right, so he's asking us YZW. So where's Y? So this is what he's asking us, YZW. Y. Yes, so this is the equation. This is the loop that is mentioned to us. How to solve this? Again, I can see that I1 is in the same direction as the loop, so this will be positive. I2 is in the, as you see, I2 is in this direction. Our loop is in this direction. So I2 will be taken as negative when I use it. Similarly, I realize that E1, this is positive, this is negative, is trying to make sure the current flows in this direction. So direction is exactly the same as the loop. So this will be taken as positive. E1 will be positive. And E2, since that is actually trying to flow the current in this direction, but the loop is trying to flow the current in this direction, E2 will be taken as negative. Now, in the complete circuit, I realize that this is positive. This is also positive. If the batteries are connected like this, for example. Sorry, let me do this again. If the batteries are connected like this, they're both going to oppose each other. Why? Because this is positive, this is positive. This is asking the current to flow this way, this is asking the current to flow this way. They're both actually working against each other. So I can see that very well over here that E2 and E1 are working against each other because they're both connected with the same positive terminal, like this. Okay, another insight towards the question. But I can see that E1 is larger than E2. Why? Because I1 is the dominating direction of the current because of the loop. Okay, so again, this is just a trick, not science. You can use it to solve questions quickly. Now, so what I can do over here is straightforward. I can subtract E1 minus E2. Why E1? Because it's in the direction of the loop. And why subtracting E2? Because it is opposite to the direction of the loop. Equals to, now again, these are the producers, the voltages, the batteries who are providing the energy, is equal to the consumers. Who are the consumers? R1 and R2. Now, since I1, R1, they are exactly in the same direction of the loop, they are taken as positive, minus I2, R2. Why? Because I2 is in this direction, loop is in this direction, so I have to add a negative sign to compensate for that, right? So this is your equation. You might see that in the marking scheme, the negative signs are swapped. It's possible that it's written like this: E2 minus E1 equals to I2 R2 minus I1 R1. No need to worry about that. That's also correct. Okay. All right. So we understand the trick, how to use it. So I'm going to use the trick to solve this question rather quickly. Okay. So he says relationship between I2, I1, I3. So pick any junction where you can find all of them together. So let's choose N as the junction. So carrying I1 is entering, I3 is also entering, and I2 is leaving, and I4 is leaving. So I1 and I3 are entering. So I1 plus I3 is entering, I2 and I4 are leaving. Straight away, Kirchhoff's first law. Current entering equals to current leaving. Second part, he says nk lmn. So let's make that loop. nk l m n. So I know the direction of the dominating battery. Okay. I understand that E1 will be dominating because E1 is trying to flow the current in this direction, and E2 is also asking the current to flow in this direction, which gives me the idea that they're both working against each other, right? Okay. Plus, do I need to involve I1? No, because there is no resistor over here, there is none over here, there's none over here. So I1 will not be participating in this equation because there is no voltage related to I1. So I'm going to ignore I1. And I see I3 again acting against the direction of the loop mentioned by the red arrows. So this will be taken as negative with this R, because we know that voltage is equal to V equals to IR. Okay. So very straightforward, I can see that E1 is a larger battery minus E2 because it's working against it. The current is in this direction, E1 is in this direction, right? Okay, simply put. And then equal, so this is the providers equal to the consumers. Who are the consumer in this loop? The resistance only, this R. But since the current of I3 is opposite to the direction of the loop mentioned by the examiner, N, K, L, M, N, so I'll have to take this as negative I3 R. Now, you will see this equation in your marking scheme probably as E2 minus E1 equals to I3R. Again, he's just eliminating this negative sign by multiplying the whole equation with negative sign. It does not matter. Both are correct. This is also correct. This is also correct. Okay. Now, moving on to third part, he says NKQN. So let me erase this. NKQN. You can pause the video at any time and try this on your own. So we have NK. Now notice I'm moving towards this direction because N, and then he mentions K. I'm not moving like this. Okay. So that's how I maintain the direction of the loop. So NK, Q, then N. So I know the direction of current that is supposed to be taken. Let's try to solve this question. No need to worry about this. I realize that the loop direction and the I3 are in the opposite direction, so this will be negative. E2 tries to flow the current in this direction. Again, it's opposite, so E2 will be taken as negative. I4 is moving in this direction. Loop is opposite, so I4 is supposed to be taken negative. So everything involved in the equation is negative. Let's try to write this. So again, the logic stands: producer equal to consumer. The shortcut, of course. Who was the producer in this loop? There is only E2. So negative E2 equals to, who's the consumer? So this is R, R, and R. This R encounters the current of I3. So this will be negative I3R, negative, because the loop direction was clockwise or anti-clockwise, and the current direction by the batteries is clockwise. So we have to compensate for that effect. Similarly, on the other hand, we have I4 moving like this, but the loop is moving like this. So I4 will be negative. So this will be minus I4 with R plus this. Once you've dealt with the first R, for example, you've dealt with this R, then you have to encounter the second R. So this will be minus I4R again. So this is going to look like minus E2 equals to minus I3R minus 2 times I4R. Now, since the whole equation has a negative sign, you can just eliminate it, and this equation is going to look like this. E2 equals to I3R minus 2 times I4R. All right. Again, no, sorry, positive. This will be plus. Again, no problem. You can choose how you write this down. Okay, moving on to this question. This is an MCQ. And if you go to the marking scheme, you will realize that there is no examiner report for this question, which means that this question was supposed to be solved by a trick. If you go online, you will realize that people have tried to apply the Kirchhoff loop rules, which is the true depth and the full understanding of what Kirchhoff first and second law are actually about, which I will explain later. Okay, but let's try to solve this with a trick. Let's try to solve this with an educated guess, because in P1 MCQs, we don't have a lot of time. What options are not possible? First, we need to realize that. Okay, so since we don't have to make guesses, there are only 4 options. Let's try to test all of them. So this is positive, this is positive, this is negative, right? Let's eliminate options based on this idea. So this current I1 can only be in this direction. Why? Because the battery tries to make sure that the current flows in this direction. So I1 is where I1 is actually drawn. The negative value of I1 suggests that when you actually applied the Kirchhoff rules, you found out that the current is not in this direction. Rather, the current has been accidentally found to be in this direction. Is that possible? No, it's not possible. It is not possible. Why? Because the direction of the current by the battery is supposed to be in this direction. The current cannot go in this direction. It's not possible. Why? Because there is no larger battery on the other side. This battery is a larger one. This is dominating. The current cannot be flowing the opposite direction to the battery. Okay. So based on this idea, the negative value of I1 is rejected. So option A is rejected. I'm not even going to test it. Let's try to move towards I3, another negative value. Can I3 be in this direction? Can I3 be opposite to this direction mentioned by the examiner? No, because in this direction or in this way, the battery is also in this direction, right? The current is supposed to be in this direction. So I3 mentioned by the examiner is absolutely right. The current cannot be the other way around. The negative value suggests that when you found it, the current was actually in this direction, which cannot be the case based on the terminals of the battery. Now, we have rejected option A and D. We are done with those options. Now we are left with option B and C. Both options seem to be correct. How? Because if I take I1 to be 0.5 and I3 to be 3.5, that means that 0.5 current comes from this side and 3.5 current comes from this side. And together they combine and form 4 amperes. Okay, good. This looks right. This looks fine. But what about the option C? 3.5 comes from this side and 0.5 comes from this side. Again, 4 looks all right. Now, Kirchhoff's first law checks out. Sum of current entering the junction are equal to the sum of leaving or the sum of currents leaving the junction. It checks out. So what do we do now? Which option should be now? We have to make a guess, educated guess. You see, the larger battery will be responsible or should be responsible for the larger current. So this I1 should be 3.5 amperes. And since this is trying to push the current in this direction and is a larger battery, 9 volts battery would have to make a lot of effort to try to push its own current or agenda into this branch, which means that this I3 should be less than I1, right? So this is going to be under these circumstances, this should be the smaller current because the battery is smaller in this branch, the current will be smaller. So based on this educated guess, our option C seems to be the right option. Okay. The examiner expected you to use your brain and the trick basically to figure this answer out. You don't have to apply the Kirchhoff rules to solve this, but in the interest of science, of course, you will find many solutions of this question online. That's why I'm giving you the true nature, the true picture based on what I've learned in engineering, what Kirchhoff law is about and how it's used. Okay. Okay, so this is the question I've drawn on the notebook, right? So I've just rearranged the currents. You can see over here. Okay. All right. Let's look at the first equation. How have I made the first equation? Now, choosing the direction of these loops as L1 and L2, there is no compulsion by the examiner or there's no compulsion by any engineering book that you can't choose the other way around. You could have selected loops to be like this, both loops to be like this. There is no compulsion. Both loops could have been in the opposite direction. One is like this, one is like this. But of course, when you do this, it involves a lot of calculations, signs, and conventions, and rules and regulations, which gets cumbersome, right? That is why I have taught you the tricks to solve these questions instead of using the actual Kirchhoff law. Anyways, let's try to learn what it actually is. Okay, so I make this loop L1, my choice, right? I make the other loop L2 my choice. It's your choice. You can choose the other way around as well, as explained earlier. Anyways, now I realize that L1 is actually in the same direction as I1, right? And it's in the same direction as I2. So I don't need to fight them. My loop direction is exactly the same as the direction of the currents. I don't need to add any negative sign. But when I consider the loop direction with the battery, I realize that my loop direction is actually entering the negative sign of the battery, which means I will have to add a negative sign with the battery. So this equation actually looks like minus 15 plus 2i1 plus 2i2 equals to 0. Then you take this to the other side, and this is what it comes out as. 15 is equal to 2i1 plus 2i2. This is my equation for the first loop, right? Let's move to the loop number 2. Now, this is one of the rules, basically, that the loop direction tells you whether the positive sign will be there or not. If the direction of the current is exactly the direction of the loop, then there is no need to add a negative sign. But if you are entering from the negative side of the battery, then of course you'll have to add a negative sign with the voltage, which of course basically what it's trying to do mathematically, the producer equals to consumer logic. It has to take that negative 15 on the other side to make it a producer. That's all it is trying to do. Anyways, let's move to this side. Loop 2. I chose this direction, my choice, no problem. But if you notice, even I3 is opposite to my choice, even I2 is opposite to my choice. So I'll have to add a negative sign for both of them. Plus, when I consider the loop direction from this angle, I see that I'm entering the positive of the battery, which means that the battery will be taken as positive. So this would go something like this. Plus 9 volts minus I3 into 2 minus I2 into 2. So I2 into 2 equals to 0. This is Kirchhoff law. Sum of all voltages is actually 0 across a loop, of course. Again, you take all these two factors on the other side, and this is what you get. Yep, this is what you get. This is the equation that you get, I3 and I2. But there is a problem. The problem is that the first equation has I1 and I2. The third equation, or the second equation, has I2 and I3. I can't solve this equation simultaneously if there are 3 variables. I can't do that. So what I'm going to do, I'm going to take help from Kirchhoff's first law, that the current entering a junction at this point is equal to the current leaving the junction. So I1 and I3 are entering and I2 is leaving. So I make this third equation, I1 plus I3 is equal to I2. Why did I do that? So that I can replace wherever I can find an I3 variable with respective I2 and I1. I want to get rid of I3, just like mathematics substitution method. Okay. So I replace that I3, or you can say in place of I3, I replace this I2 minus I1. Then I solve it with algebra and I get this equation. That 9 volt is equal to 4 times I2 minus 2I1, and of course the rest of the equation. Now this is carried from the first part, 15 2I2 2I1, which was this equation. This was equation A. This is equation B. Now I can solve it simultaneously, but since this is not a mathematics exam, I'm not required to do this. Okay, what I can do is use the help of the calculator, which I've taught earlier as well. Now, let me show you on the video what I've done. So this is going to be a calculator, right? I'm going to show you what options to select. So you go to mode, right? You press 5, and then you go to, let me start it from the beginning. You press mode, then you press 5 for equation, then you press 1 for this equation, which is this one, ax, b, and y equals to cn. Okay, right. Now you get this, okay, you get the simultaneous block. Now let me write this equation down for you. This is the equation that we're trying to solve. Be very careful that how to use the calculator for this. 9, or the variable that has no x and y. Let's say this is the equation that you're actually looking at. So this is 4x minus 2y equals to 9. And this is 2x plus 2y equals to 15. This is what the equations are actually looking like. Okay, so I'm going to write these equations down on the video. Okay, so this is what you get. So you're getting 4x minus 2y equals to 9 and 2x plus 2y equals to 15. Okay, these are our two equations. Now observe how we are going to put them over here. So I put 4 for x, minus 2 for y, and 9 when it was on the other side of the equation. Okay, then 2, then 2 again, and 15. Now please be advised that we understand that this was I2 and this was I1. Your x was represented by I2 and y is representing I1. Be careful, okay, because this is where you've written it down at the first. This is your I2 and this is your I1, right? Be careful. Okay. Now let's see what happens. Press equals to, and you get the first answer, that is 4, which means that I2 is actually 4.0 amperes. This is my I2. And I1, the first answer, which is y, will be, let's see, press equals to again, it will give you the second answer. Now the y comes out as 3.5, which means I1 is actually 3.5 amperes, right? Now I've written this on the solution, so I'm going to clear this out and go back to the video. So using, of course, calculator, I've shown you how to do that. I get these answers. Now then I put this back into this equation, okay, and I get this 0.5. Now all answers are here, 4 ampere, 3.5 and 0.5 based on this option C. Now again, consider that if you were to make this equation, if you were to make these equation and you forgot about the calculator, you try to solve this by simultaneous method and eventually substitution, elimination, whatever you're comfortable with, you find these answers, it will take you minimum 5 to 7 minutes to solve this MCQ, which means that the examiner wanted you to use the trick that 15 volts would have caused for the higher current and 9 volts would have caused for a lower current. Okay. All right. I hope that we understand this, and we also understand how the full force or the full nature of Kirchhoff law actually is. Okay. All right.